Pardon me. All right, good morning, ladies. Not a very big group today, so it looks like Fridays are not a good day to have class, but that's okay. I didn't want to get out of bed myself, so it's okay. So unfortunately today we're gonna have a kind of an awkward day because we're gonna be finishing material yesterday for the exam that's on Monday. So we have kind of a day where we're gonna start all the material for the next chapter stuff. And then Monday we'll have the exam, and then Tuesday we'll come back to all this kind of stuff. So today we're gonna go ahead and start the next chapter, which is chapter 16. So now we're going to start moving into what we're going to spend the rest of the class on, which is all the new material, which is no longer going to be Newtonian type physics, which is now going to be what's known as electromagnetism. So this is what I was talking about on the first day of class, where we're not really going to have our intuition anymore. So basically now we're going to be dealing with things that are called fields and fundamental particles and things that we can't see. So we're going to have to rely a lot more on our physical principles as well as our mathematics to actually understand what's going on. So we won't have that intuition of things going under parabolic motion and all kinds of different things anymore. So this chapter, it's going to take a little bit of a leap of faith from you guys at a few stages. Especially when we start talking about fields. It's kind of a hard topic to start to grasp. So we'll spend some time talking about fields when we actually get there, when we start talking about electric fields. But just to let you know kind of what we're on our way to. Okay. So let me share my screen. Here's my screen. So today, again, we're starting chapter 16. So chapter 16 is all about electrostatics. So basically what that means is we're going to have charges which are non-moving most of the time. And these are going to create what are known as constant or static electric fields. So talk more about this. So what you know, and what we talked about in physics 175 was all matter was quantified by one single quantity, which was intrinsic, which means it was inherent to that object, which is what we called its mass, right? So all matter had this one quantity mass, and then we knew everything else about it based off its mass. So if we knew its mass, we knew its gravitational force, and then under different contexts, we also knew how it was going to move and etc. But in 176, we're going to start adding on top of this. So things don't only just have mass anymore, but they're also going to have other intrinsic quantities as well. So things that are actually inherent quantities for them, and this is what's called charge. They also have something called spin. We might talk about this a little bit at some points, but for now, let's not worry too much about spin. So all things have charge. So charge, unlike matter, comes in three different flavors. So what are the flavors of charge? So we're going to have positive charges, negative charges, and neutral, which means they have no charge to them at all. Now, again, this is different than mass. Mass pretty much has two flavors. It's either positive or zero, right? So neutral. Units of charge are what we call a Coulomb, which is going to be denoted by a capital C here. So this is what's called a Coulomb. So basically all matter then is going to have charge, and then charge is going to add another type of force because charges will also have forces acting between them as well. So normal matter is made up of three fundamental constituents, which are the electron, the proton, and the neutron. So let's kind of take a little bit of time to talk about the electron, the proton, and the neutron, and think about its mass, their charge, and see what you remember from your chemistry classes. Okay. So anybody remember the mass of an electron from your chemistry class? No, that's okay. The mass of an electron is 9.11 times 10 to the minus 31 kilograms. So this is the mass of an electron. What about a proton? Anybody remember the mass of a proton? No. That is 1.67 times 10 to the minus 27 kilograms. And what about a neutron? Anybody remember the mass of a neutron? No. It's roughly the same as the proton. They're slightly different, but for the most part, they're the same. So it's about 1.67 times 10 to the minus 27 kilograms. So this is a neutron. So what about the charge? Anybody remember the charge of an electron? How about this? Anybody remember if it's positive or negative?
-1.
-1 in a particular unit, but we'll get there. So in the fundamental units, it's negative 1.602 times 10 to the minus 19 coulombs. Or what Callie's thinking of is what we just call E, and we'll get there in a second. So E is what's known as the fundamental charge, which is 1.602 times 10 to the minus 19 coulombs. So in terms of the fundamental units, Callie's right, this is -1e. Okay. What about a proton? What's the charge of a proton? Is that one positive or negative?
Positive.
That one's positive, good.
Wouldn't
So
it
that
be
one
the
actually has
1.6?
exactly the same charge as the electron, just positive.
Just without the negative.
Just without the negative, exactly. So in terms of the fundamental charge, this would be a positive E. Good. And then the neutron has 0 charge to it. So it says 0 coulombs. Good. So I mostly bring up the charge and the mass and things because we can see that what? The proton is huge compared to the electron, right? It's about 1,000 times heavier than that of the electron. The neutron is exactly the same mass, so it's the same mass as the proton. But the charge of the electron and the charge of the proton are the same, just one is positive and one is negative, where the neutron has 0 charge to it. So it turns out that the smallest charge that you can actually have in nature, somewhat true, turns out to be actually the charge of an electron and the charge of the proton. So we define here what's called E, which is the charge of the electron and the charge of the proton, as what's known as the fundamental charge. Fundamental charge. Which means that all normal matter is going to have some integer multiple of charge based off of this number, right? So what this means then is that all matter that is charged has a charge that is an integer multiple of E. Okay. We'll talk about why that is in a little bit. But basically anything that's charged then is either going to have an excess number of electrons or an excess number of protons, which means that all of the charge or the amount of charge that the object has to be then an integer multiple of this fundamental charge. Now, it turns out that actually the fundamental charge isn't the smallest amount of charge you can have because we have things that exist in nature, which are called quarks. Anybody know what a quark is? No. So a quark is actually the building block of a proton and a neutron. And actually for all what's known as baryonic matter, but that's okay. So basically what a quark is it is the basic building block of these fundamental particles. So for example, a proton is made up of what are known as 2 up quarks and 1 down quark. But it turns out that a quark actually has a fraction of charge of this fundamental charge. So the reason I bring this up, because basically in reality, a quark, which is the building block of these guys, has a fractional charge of the fundamental charge E. So if I remember right, it's either 2/3 of E or 1/3 of E, depending on what type of quark it is. But in nature, there are actually 6 different types of quarks. There are 6 types. Yeah, I think there's 6. So there are 6 types of quarks. ones we care about mostly are going to be your up quark and your down quark. So again, for example, if I was dealing with a proton, so a proton is actually created from 2 up quarks and 1 down quark. So this is actually the basic building block of those. So yeah. So actually, most of the fundamental particles that we talk about aren't actually fundamental particles. They're created from other fundamental particles, except for the electron. But that's fine. I don't want to confuse you too much. So anyways, so this is normal matter. So again, normal matter is going to be created by these objects. These objects, again, have both mass and charge to them. So how do I know, first of all, that there are multiple types of charges? Okay. That's a good question. So for example, let's watch this kind of video here. I know there are different types of charges because, for example, let's say initially if I watch this, this is a glass rod which is charged up. So this glass rod, actually no, it's a plastic rod, sorry. This plastic rod has a negative charge to it. And then initially the ball here is going to be attracted to it. But what will happen then is the ball, as this is moving towards it, will end up touching, and then what we'll watch is that this thing will actually end up rebounding away from it. So it actually gets repelled from it. Okay. So if I watch this again, I don't want a subscription, thank you very much. Okay, so if I watch this again now with charges, and we'll talk about how this actually works. So what's actually really happening is initially, this thing is being charged via what's known as induction. We'll talk about what induction is in a second. So what happens then is that all of the negative charges are being repelled inside of the object. So this starts off neutral, but the positive charges are being attracted to these negative charges. The negative charges then are being repelled, which causes this overall attractive force to it. Now, as it moves in, what's happening at this stage then is, thank you, I still don't want a subscription. Go away. Okay, so what happens then when it touches it, it's now being charged by what's known as conduction. And again, we'll talk about what that means in a second. But basically what happens with conduction is the charges then distribute evenly amongst the 2 objects, which means that they now both share the total charge at which this thing originally had. So now what happens is that this original neutral sphere becomes negatively charged. This one is also negatively charged. And what happens in that case then is that it switches over from an attractive force to now a repulsive force. Thank you so much for not cooperating. Which then causes it to kick away, right? So in this case, what's happening now is I have negative charges here, which is now causing a repulsive type force. Right? So basically, I know from nature that things have opposite charges, or at least I have multiple different types of charges based off of the type of forces to them. So in nature, we find is that we can see different types of charges based on forces. So some things, again, will be attracted to each other, some things will repel from each other, and some things will have zero reaction to them. Those are going to be the neutral objects. So an interesting question then is, how do I charge an object? So how do we charge an object? So the first way we're going to charge an object is using what's known as static electricity. So what is static electricity? Well, static electricity happens when you take, say, 2 objects and you rub them together. So for example, if I took glass and I rub it, you might know how to spell rub, there you go, no W. And you rub it, say, with silk. We rub with silk. Right? What happens in that case then is it causes the originally neutral glass rod, so let's say here's my glass rod initially, which had no net charge to it, so this had 0 charge. And then I'm going to rub it with the silk, so let's say here's my silk. It's a horrible silk, but whatever, that's my silk. What happens afterward then is that the glass rod then becomes positively charged. So ultimately what will happen is that this lapse rod becomes positive. Or if we took, say, a plastic rod, and then we rubbed it with fur, what will happen in this case then is here's my plastic rod, here's my fur, there's the hairy fur, great. So initially this thing has 0 charge to it, so it has 0 coulombs. What will happen in this case then is my plastic rod will become negatively charged. Okay. But over here, if I look at my silk, so let's say here's my silk, what I'll find is that my silk ends up being overall negatively charged, even though my silk initially had 0 charge to it as well. And then over here, my fur, say here's my fur, which again had 0 net charge initially. Well, the rod is negatively charged, then the fur over here is going to end up being positively charged. Okay. So basically what's happening here is what's called static electricity. So the way static electricity works is, bring up this next one. Let's say I had like a balloon here and a wool sweater over here, and I'm going to take the balloon and then I'm going to start rubbing the wool with the balloon, right? So what's going to happen then is that what? Static electricity occurs because one of the objects is going to strip off electrons. So what's happening here is that initially the balloon, let me reset this, has 0 net charge because it has what, 4 protons and 4 electrons. The sweater has 0 net charge because everything, all protons are coupled with an electron. But then when I start rubbing the sweater then with the balloon, it strips off all of these loosely bound electrons which are on the wall, which then causes the sweater to become positively charged, the balloon to become negatively charged, which then causes an attractive force between the two. But simultaneously, I could take that balloon and then push it against the wall, and I can actually have it stick against the wall, even though the wall is still neutral charge, where the balloon has a negative charge to it, but the wall has 0 net charge to it. So this is called polarization. We'll talk about how this works in basically a second. So what static electricity does is static electricity actually will strip off loosely bound electrons from an object. Okay. So here it's easy to strip off the electrons from the wool. Here it's easy to strip off the electrons from the glass. And here it's easy to strip off the electrons from the wool or from the fur. Another example of this would be in the wintertime, people like to scuff their feet when they walk across the floor. So as he scuffs his feet, what will happen in this case is he actually strips off electrons from the floor, which causes him to build up with an overall charge, which causes you to get a shock. And we'll talk about why you get a shock later in the semester. But again, whenever you walk across the floor, you're scuffing your feet, you're stripping off the electrons from the rug, causing you to end up with an overall charge. And then when you go to touch something like a door handle, you dissipate those charges, all those excess charges, through the metal of the door handle, which causes that shock. You can move his hand even closer and get a much better charge on that. Okay? So this is what we call static electricity. So static electricity then is the stripping off. So this is the stripping of electrons from a material. So this is what we call static electricity. So again, here, what's happening is we're stripping off the electrons from the glass. Here, we're stripping off the electrons from the fur. And then in this case, he's stripping off the electrons from the rug. Okay. Now, the reason this happens is because if we think about the Bohr's planetary model of an electron, what you have is the nucleus at the center, right, which has basically all the positive charges, as well as the neutral charges. Inside of here are neutrons. And then we have the orbital levels, which then have electrons in them, right? So here, let's say I have 4 electrons here, and then let's say there's 1 excess electron out here. So basically what will happen is, if I have something like this, which has 1 excess electron out in the outer valence shell, so this is our outer valence shell, since this is the single electron which is sitting in this valence shell, what will happen is it's going to be very loosely bound to the atom itself and is easy to strip off then from the material. So as I start to rub against this material, the atom then has this extra unpaired electron, or maybe a couple unpaired electrons, which are very loosely bound to the rest of the atom, which allows it to easily be able to be stripped off. So by rubbing this thing, I can easily pull off this electron. As opposed to if I was dealing with something else, you know, say like an inert gas or something like that, there, all of the shells are basically either full or almost full, which means that all of the electrons are very tightly bound to the atom itself, which makes it almost impossible to rip these things off. Right? This is the difference between what's known as a conductor versus an insulator. We'll talk more about these, but insulators have very tightly bound electrons, which doesn't allow for these things to be stripped off very easily, where a conductor has very loosely bound electrons, which means they can be stripped off easily. So this is what static electricity comes from. So this is one way we can actually charge an object. We can charge it via static electricity. Another way we can charge an object is by what's known as induction. So what's induction? So induction is the charging of an object via indirect contact. Indirect contact. So that was the first part of the video. So in the first part of the video, which is also the same thing we did in the lab, so let me bring up the lab simulation here. So in this case, if I introduce, say, this glass rod, what's happening in this case is I'm getting induction. I'm getting a charge separation. So what happens in induction is basically I get a charge separation or a polarization due to the fact that the negative charges here are going to be attracted to the positive charges, where the positive charges will be repelled by these positive charges, which means that all the negative charges will move to one side of the object, leaving all positive charges on the other side. Okay, so this is what's called induction. Now, what's happening here is this thing starts off electrically neutral. It is still electrically neutral. All that's happening is I'm getting charge separation. So this still has an overall net charge of 0. It's just this side ends up being negatively charged while this side is positively charged. It's what's called polarization. So if I wanted to end up with this thing being overall charged, what I would have to do would be cut this thing in half, for example. So if I wanted to make, say, something with a positive charge and a negative charge out of this aluminum can, what I would have to do at this stage is simply cut the aluminum can. So if I wanted to have this thing be charged, again, I would just chop this thing in half. One half would be negatively charged, the other half would be positively charged due to this charge separation. So this is what we call induction. So here I'm not directly contacting the object, I'm just causing the charge separation within inside of the object. So this is called induction. So here if I took, say, a glass rod, so here's my glass rod, which again has positive charges, and I bring that near some sort of neutral object. Here's my neutral object. What happened is then I get all these negative charges built up on one side, positive charges built up on the other side, but this thing still stays with 0 net charge. So again, if I want this thing to actually end up being charged at the end of the day, all I would have to do then would be, say, cut this thing in half. So that after I cut it in half, I'm going to have one half, which is going to be negatively charged overall, and the other half, which is going to end up being positively charged. This is what's called induction. So here we're charging via induction, which is the charging via indirect contact. The last way we can charge something is what's called conduction. So conduction, where conduction is charged via direct contact. So that was the second part of that video there. So in the second part of the video, what happened was we took our plastic rod, in this case I'm going to use a glass rod, which again is, say, positively charged. Here is my neutral object again. So again, now what I'm getting is negative charges, say, on this side, positive charges onto this side. So basically what happens is under conduction, when I touch these two things together, so let's say here's my rod, again, here is my neutral object, what'll happen then is that what? Some of the negative charges from the object here, my neutral object, will move then onto the glass rod. So what'll happen here is, say, my glass rod again has 4 positive charges, but now a couple negative charges are going to end up moving onto my glass rod, meaning that I have too few less negative charges on the rod itself, or on the neutral object. So now my neutral object will end up having, say, 4 negative charges, but it's going to be left with, say, 6 positive charges. So that way, when I pull them apart, let me know, new change. So now let's pull these guys apart. What'll happen then is now that my glass rod will now be left with, what, 4 positive charges, with now 2 negative charges, which means that 2 of these negative charges are going to combine with then these positive charges to create this thing having an overall +2 positive charge, or my neutral object is now going to have, again, say, 6 positive charges, but only 4 negative charges, which means that this one's going to be left overall with a +2 positive charge as well. So again, initially what's happening is that my glass rod comes in, has an overall charge of, say, +4. This one has a charge of 0. After they touch, they're going to share charge so that this now has +2 charge, this has +2 charge. Okay. But all of these things, happen in such a way that the total charge must remain constant at all times. Okay? This is what's known as conservation of charge. What are you doing? So conservation of charge. So what conservation of charge says is that the net total charge initially must be equal to the net total charge finally. Or we can say that the sum of all the charges initially, you're being recorded right now, is equal to the sum of all the charges finally. Excuse me, I have to get rid of a child. Go, 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 go. Go eat your breakfast, Mr. Starving. So that was my eldest. You can see him. All right. So good. So this is what's happening. So again, this is what conservation of charge said. So this is actually a new conservation law for us. So this is a brand new conservation law. So now we have conservation of energy, conservation of momentum, conservation of angular momentum, and now conservation of charge. So this is a new conservation law. So all this says is, again, when I'm charging something via conduction here, what'll happen is, again, if it starts off with a total net charge of 4, say initially before these guys touch, so this guy has a positive charge of 4, this guy has a charge of 0, so initially the total net charge is 4. After they touch, charges move around, so that now this one has 2 charge, and this one has 2 charge, but again, the total net charge between all of these has to still be 4. Okay? This is what we call conservation of charge. So these are the different ways that I can actually charge something. So again, we can do induction, where this is what's known as polarization. So here I get charge separation via what's called polarization. Polarization. Or here, direct contact, where these guys are now sharing charges. Okay. Now, the way that this is going to happen, whether things are going to share charges or not, typically depends on the type of material that we're looking at. So pretty much all material is going to fall under one of 2 classes. So all, I'm going to put all in quotations here. Matter falls into one of 2 categories. Now I'm going to say all with quotations here because this isn't quite true, because we do have other classifications, which I'll briefly talk about. But basically, all material is going to fall under one of two categories. There's going to be what's known as an insulator and what's known as a conductor. So again, we kind of talked about these, but let's talk about them a little bit more in depth. So what's an insulator? So an insulator is a material whose electrons are tightly bound to an atom. An insulator is a material whose electrons are loosely bound to an atom. So basically, what's the difference? So the difference is that here in the insulator, what happens is, since the electrons are so tightly bound to the atom, that single atom basically has those electrons. Okay? So basically, what happens here is that the atom is the sole owner of that electron. Where in a metal, what happens is, since the electrons are so loosely bound, all of the atoms will share those same electrons. So all atoms share the electrons. So basically what happens is, in the conductor, the electrons are free to move throughout the conductor at will. So here the electrons are free to move around the entire material. So let me kind of show you another simulation and show you what I'm talking about here. So here is a conductor, and then here is an insulator. So you can kind of see on here, so here is my atoms, which in this case are just a single positive charge, which has an electron basically orbiting about it. And then here you can see in the conductor, the electrons are moving around wherever they feel like moving. So basically, they're not bound to a single atom. They're being shared by all possible atoms. So what'll happen? So basically what'll happen then is, if I took a charged body and I bring it near here, what you can see then is that what? In the insulator, I'm simply getting polarization. So what's happening is that now the negative charges are being slightly pushed away from the atom itself, causing a charge separation. So this side becomes more positively charged, this side becomes more negatively charged, but they're still tightly bound. So I'm only getting a small charge separation. So the material itself is doing what's called polarizing. In the conductor, what's happening then is, since these negative charges are being repelled by these negative charges, all the negative charges then will move to the opposite side, so that this side becomes, on average, negatively charged. This side will become positively charged, which gives us that polarization throughout the entire material, which is what we saw going back to our induction. So the induction here will only really work if I have a metal, i.e. a conductor. So this, what we drew here, won't work with an insulator. So in an insulator, the only thing that's happening is we get this small charge polarization. The conductor is what allows all the negative charges, say, to move to one side, leaving only positive charges on the other side. Okay? So this is the difference between a conductor and an insulator. So conductor, the electrons are free to move. They move throughout the entire object. So if I brought a charged object near them, all the electrons will move to one side versus the other side. In the insulator, we get a small charge distribution, meaning we get this small polarization. But since all the electrons are so tightly bound to the atoms themselves, I can't force all of them to one side. I only get this small polarization. Okay, so this is the difference between the two. So in an insulator, they're very tightly bound. In the metal or in a conductor, these things are very loosely bound, meaning they can move wherever they feel like moving to. Okay. So an insulator, what happens here is that, again, our material only polarizes. So here, the material will slightly polarize. So again, if here's my material, my insulator, what'll happen here is I'll get positive charges, and then I'm going to get a small charge separation with the negative charges, which is what we call polarization. So this is a insulator. Now, most materials end up being insulators. This is basically going to be most material. So your plastics, glass, wood, different things like that, these are all basically insulators. Again, what happens in a conductor is going to be what? Again, if I brought something, say, positively charged near it, here's then my conductor. What happen then is we're going to get what? All the positive charges end up being built up on this side. All the negative charges then will be attracted, so they're all going to move to this side. So conductors end up being basically just metals. So pretty much whatever is a metal is going to be a conductor. Okay. Now there are different types of materials. These are not the only ones that actually exist. As far as our class is concerned, these are the only ones that are going to exist. So basically either everything's going to be an insulator or a conductor. But in reality, we can also have what are known as superconductors, or what are known as semiconductors. So ultimately, we don't have just insulators and conductors, but we have insulators, conductors, superconductors, and what are known as semiconductors. Briefly, a superconductor is a type of material where the resistance goes to zero. We'll talk more about what resistance is later. But typically what happens is in a metal, it has a non-zero resistance to it. So meaning that there's a little tiny bit of resistance, but in a superconductor, basically what happens is that the resistance actually goes to zero at some stage. Now, typically what happens is that for this to happen, the temperature has to go ridiculously small. So the temperature of the object actually approaches 0 Kelvin. So it has to be very, very low temperature. Semiconductors is basically a in-between between an insulator and a conductor. So this is kind of a hybrid, if you want to think of it as a hybrid, of an insulator and a conductor. Semiconductors are used all the time in basically realistic situations. So a lot of computers and a lot of hardware is basically built off of semiconductors. But again, as far as this class is concerned, we're not really going to talk about these, but just note that they actually do exist. So everything's not as cut and dry as either an insulator or a conductor. But again, as far as this class is concerned, a conductor will always be a metal. And then basically anything else will be an insulator. So this is basically going to be anything else. So anything that's not a metal will be an insulator. So good. So again, we can charge things one of 3 ways. So basically via static electricity or induction or conduction. And the way that it's done under conduction and induction is going to be based on whether the fact it's an insulator or conductor, as well as static electricity. Static electricity is also dependent if it's an inductor or a conductor, or an insulator and a conductor, sorry. Again, an insulator, since all the electrons are so tightly bound, they don't want to give up their electrons, but they're going to gain electrons, as opposed to a conductor, which easily will give up the electrons. So good. So now that we know that these things actually feel forces, how do we define the force between them? So this is what's known as the Coulomb Force. So this is what we saw in lab. So let's talk about the Coulomb Force. So the Coulomb Force, also known as the electric force. So what does the Coulomb Force say? Well, the Coulomb Force says that what? let's say I have two charged particles where this one has a charge of Q1, this one has a charge of Q2. These guys are separated from center to center by a distance of r. Then what the Coulomb's law says is that the magnitude of the electric field, or the electric force between the two of these, is given as 1 over 4 pi epsilon naught times Q1 times Q2 divided by r squared. Or we usually define this then to be K times Q1, Q2 divided by r squared, where K is equal to 1 over 4 pi epsilon naught is equal to 8.99 times 10 to the 9th newtons meters squared per coulomb squared, which for us, we're just going to call 9 times 10 to the 9th newtons meters squared per coulomb squared. Okay. So what this means then is that epsilon naught is then equal to 1 over 4 pi times K, which works out to be about 8.85 times 10 to the minus 12th inverse of this. So it's going to be a coulomb squared per newton meter squared. Epsilon naught is what's known as the permittivity of free space. So permittivity of free space you can basically think about in one of two ways. This is kind of like how easily does what we're going to call the electric field permeate the space. Permeate the space. And it's basically a measure also of the strength of the field, or the strength of the material. So strength of E in the material. So this is called permittivity of free space because this is only true in free space. So in a vacuum, basically. What will happen then is that this number, epsilon naught here, is going to change, be different depending on if I'm in a material or not. So for example, if the electric field is in a insulator versus in a metal, then I have different strengths of the field based off of that. We'll talk about this later. So don't worry too much about that for now, but just note we have this thing, epsilon naught, which is called the permittivity of free space. Now, let's say this has a mass m1, this has a mass m2. So notice the structure of this is very similar to the structure of the gravitational force, where the gravitational force is equal to G, which is Newton's constant, times m1 times m2 divided by r squared. So mathematically wise, these two things have exactly the same structure. So it's basically the product of an intrinsic property, which in this case is the product of the intrinsic property of the charge, where in this case it's the intrinsic property of the mass, divided by the distance squared. So it has exactly the same structure. Now what's different though is that the gravitational force is always attractive. So meaning that if I was looking at the gravitational force, M1 is going to be gravitationally attracted to M2, and M2 is going to be gravitationally attracted to M1. So these things will always be gravitationally attracted to each other. But remember that mass is always positive, meaning that we always have a positive mass, so these things will only be gravitationally attracted to each other because they have a positive mass. But charge now, we know charge is a little bit different, where charge can be either positive, negative, or zero. Right? So the type of force we're going to get here is actually going to be dependent on how these two charges are related to each other. So unlike gravity, where they're always going to be attracted to each other, for electricity it's a little bit different. So now I have to think about not only what is the mass or what is the charge that these things have, but how do these charges relate to each other? That's going to determine the type of force that it ends up being. So let me switch to a new page so that way we're not too cluttered. Okay. So again, so what happens here is that here, let's say this is Q1, this is Q2. So here's Q2, here's Q1, here's my distance R again. So again, this is K Q1 over 2r squared. So what ends up happening here is that what? It turns out that like charges repel. So anytime I have like charges, what'll happen then in this case is I get a repulsive force. So this is going to manifest itself as a repulsive force. So for example, if I have a positive charge here with a positive charge here, what will happen then is that the force on Q1 from Q2 will be in the opposite direction. Oops, 2 with 1. There we go. So this is F21. These guys will be repulsed from each other. Okay. Now, just like gravity, the direction of the force will be along the line which connects these two charges. So the direction of the force is along the line connecting the charges. So here, instead of these guys being attracted to each other, they're going to repulse from each other. This would also be true if I have, say, two negative charges. So if this was a negative charge here, and this was a negative charge here, again, these guys are going to be repulsed from each other. However, it also turns out that unlike charges, attract each other. Which means whenever I have unlike charges, this is going to result in an attractive force, just like gravity. So here, if I had, say, again, Q1, here is Q2, again, separated by R. Now, in this case, if, say, this one is a positive charge, this one is a negative charge, now I'm going to feel that attractive force. So now F12 will be in this direction, and then F21 will be in this direction. That would also be true if I had, say, this one was negative charge and this one was, say, positively charged. Okay? So as long as we have unlike charges, that will result itself in an attractive force. If we have like charges, this will result itself in a repulsive force. Okay? So this is called Coulomb's law. This is true for only two single point charges. So if I have 1 point charge here and 1 point charge here, this is then Coulomb's law. But what happens if I have more than 2 point charges? So let's say I have, stop doing it. So let's say I have one charge here, Q1, one charge here, say Q2, another charge here, say Q3, and let's put one more charge on here, say Q4. Okay. So let's say what I want to know is, what is the overall net force on charge 1? So how would I do this? Well, let's for funsies say that Q1 has a negative charge, and Q3 also has a negative charge. And then let's say Q4 has a positive charge, and Q2 has a positive charge. So basically, so let's say this distance here is going to be R14. This distance will be R12. And then this distance is going to be R13. Okay. So in this case, since this is a negative charge with a positive charge, we know here then this is going to be attracted to it. So F14 is going to point in this direction. This is also a negative with a positive, so this one's also going to be attracted in this direction. So this is going to be F12. But 1 and 3 are both negative charges, so it's going to be a repulsive force. So it's going to point off in this direction. So this is going to be F13. Okay. So the total force that this thing is going to feel then is going to be the individual Coulomb forces between all of the charges. So F12 with F13 with F14, then vector sum together. So this is going to be F13 plus F12 plus F14, all vector sum together, so that the total net force will be the vector sum of all these together, which say would put off in, say, this direction. So this would be the total force then on F1. Okay. So my total force then is simply going to be F12 plus F13 plus F14. Okay. But what happens if I have a fifth force, or a fifth charge, and then a sixth charge, and then a seventh charge? So in general, we're going to write this then as equal to the sum of the force 1I, where we're going to sum over I. So this is then equal to K times Q1 times the sum of Qi divided by R1I squared. Okay. So this is what we call the magnitude of the force on 1. Okay. So this is what's known as the superposition of forces, or the superposition principle. So all this is the fancy way of saying then that the net force on, say, charge 1 here is simply equal to the vector sum of all the individual forces acting on it based off of all the other charges. Now, is this anything different than what you did in 175? Of course not. Right? So if you had a gravitational force pulling down with a tension pulling in this direction with something else pushing in this direction, then the net force acting on the object was just the vector sum of all the different forces acting on it. It's the same thing. Here we just give it a new special name, call it the superposition principle, just to wow you. Okay, so, but it's ultimately the same thing. So all it says is that the total force acting on F1, or on charge 1 here, is now just all the individual Coulomb forces between all the other possible charges, vector sum together. But again, we have to be a little bit careful because now, again, the sign of the charges matters. So I have to pay attention to, is this a negative charge and is this a negative charge? So is that a repulsive force? Is this attractive force, and et cetera? Unlike gravity, which is simply, they all pull towards each other. All right?
Well, I assume like the charge would be like when we're adding the forces together, determine whether it's like plus or minus.
Oh, typically it's going to be given to you. So you would have to be told, you know, this charge is, say, positive 5 coulombs. So.
But like when we're summing the forces together, like you did in that equation right there. So we don't have. You said pay attention to like if they're repelling or attracting. Correct.
So that's going to determine the direction of the force. That's right. So basically, as I have drawn on the figure itself, so here where I'm drawing, say, F13, I'm using the fact that these are both negative charges, which gives me that repulsion force.
Oh, okay.
Okay. And then here between for F12, so between Q1 and Q2, one's a negative charge, one's a positive charge, so that's giving me my attractive force in this case. So basically what'll happen is the same thing. We're going to draw a free body diagram, but we're going to draw the directions of the forces based off of how these charges relate to each other. Then once we draw those and we know the directions, now we know that, let's say if I set up a coordinate system on here, so let me put on a coordinate system. So if I call this, say, my y-axis and I call this my x-axis, then in this case I would know that F13 points in the positive y direction, F14 is in the positive y direction, but F12 has 0 y component. And then in the x direction, F13 is a negative x, F12 is positive x, and F14 is also positive x. So we mostly only have to pay attention to the signs when we're drawing the vector lines for them. And then after that, we just use our coordinate system to then draw what we actually have on there. So that's a good question, which brings us into our first example question. So let's do an example, which of course I didn't open here. We'll do that now. Online examples, there we go. 2. Example 1 or example 2? I think example 2. Sorry, usually I have these open. Got distracted by my kids attacking me this morning. Okay. Hello, computer. All right, well, anyways, let me kind of see it there. There it goes. It's finally opening. Great, here we go. Okay, so here we have an array of particles, such as this, and what we want to know is what is the force on this third charge here? okay? So basically, what we have is, from here, we have Q2 is at the origin, according to this coordinate system, which has a charge of 50 microcoulombs. Q1 is on the x-axis at 52 centimeters away from the origin, has a charge of negative 86 microcoulombs. And then Q3 is on the y-axis, which is 30 centimeters away from the origin, which has a charge of 65 microcoulombs. What we want to know in this case then, again, is what is the total charge, or sorry, what is the total force on Q3 here? So this is what we want to know. So let me draw it on here. Good, so here, so let's say this is Q3. Down here is going to be Q2, and then Q1 was over here, right? So Q1. So this one, and this one. So bring my picture so I can remember all my. So 50, 86, and 65. Okay. So this one was 65 microcoulombs. This one was 86 microcoulombs with a negative. And this one was 50 microcoulombs. And then I was told, if I could draw a straight line. Good, so I know this distance here. So let's call that R23 was equal to 30 centimeters. This distance from here to here, R21 was equal to 52. Yeah. 52 centimeters. So Pythagorean's theorem then tells me that this distance across here is then what, 60? Yeah, 60 centimeters. So let's call that R13 is equal to 60 centimeters, which makes this a 30-degree angle. Okay, great. And this is my y-axis. So again, here's my y-axis, and here is my x-axis. So again, what I want to know then is what is the net force on the third charge. So this is what we want to know. Good. So now what we now know is that to find the net force, we have to use the superposition principle. So what this means then is we want the force on 3 by the first charge plus the force on the third charge by the second charge. So this is what we want. Okay. Now, inherently, this is going to be a vectorial expression, which means that what we have to do then is split this up into components. So what we want then is the x component of the force on 3. So this is going to be the x component on 3 by 1 plus then the x component of 3 by 2. And then we also want the y component, which is going to be the y component of 3 on 3 by 1 plus then the y component on 3 by 2. Okay. So let's draw then our vectors. So let's see what this looks like. So first off, again, let's look at the force between 1 and 3. So here we know 3 is a positive charge. We know 1 is a negative charge. So does that result itself in an attractive force or a repulsive force?
Attractive.
Attractive, good. So in this case, we're going to draw our force down in, if I could actually draw something, close enough, in this direction. So this is going to be F31, right? So F31 is going to point in the positive x direction, but in the negative y direction. Good. And then from here, we can see then that's what? Q3 is a positive, Q2 is also a positive. So is that an attractive force or a repulsive force?
Repulsive.
Repulsive, right? So in this case, I know that this force is going to point in this direction. So this is going to be F32. So F32 will only be pointing along the positive y-axis. That looks horrible. So hopefully everybody can see that. Great. So now the vector sum between these two forces then is going to be the net force, where the net force then is going to point somewhere off in this direction. So this is going to be the total force on 3. So F3 should point in this way. Okay. So now what we want to do is use this. So what we want to do now is what? Break this total force. We want to break it up into components of the x direction and the y direction. So to do that, let's move our coordinate system from this original coordinate system to something more useful, which is going to be here. So let's put this my x-axis, and this is now going to be my y-axis. Okay. So basically all I'm doing is now I'm saying that what? X points this way, y points this way. So that according to this coordinate system, F32 points this way, 1, and now 31 points this way. Are you back again?
Yeah.
Yeah. Teaching class. Can you go check on your mother for me? And do you want to get in trouble? 1. Now, what I know is what? This is 30-degree angle, which means that alternate interior angles are the same, so this is also a 30-degree angle. So this angle here is going to be 30 degrees. Okay. So good. So from here, all I want to do then is what? Use
Were we
this.
given
to
that
then,
angle?
I'm sorry?
Were we given that angle to begin with?
Well, I had it drawn on a diagram, but what I originally gave you was this distance, and then this distance, and then you could calculate this distance, and that this was 30 degrees.
Okay.
But in the original picture that I gave here, I had already given that angle of 30 degrees. So yeah. So either way you want to think about it. So either I can give it to you or you can calculate it, but overall it's the same thing. Always okay? So basically, now we're going to use these. So now we're going to look for the x component and the y component of each one of these guys, and then simply sum them together to then find the components of the net force. Where again, we said the net force should point off in this direction. So this should be the net force, F3. And then we can find its magnitude and its angle. So under all the usual vector stuff we've done before, or at least you've done in 175. We haven't done it actually yet in this class. So let's look at the x component first. So let's do F3x. So again, according to this, this is going to be the x component of F31 plus then the x component then of F32. Now, as we can see from our diagram, F32 has no x component because it only points along the y direction, so we automatically know this is going to be 0. So this is then going to be equal to F31 times what? So according to this angle here, to get the x component, do I want to take the cosine portion or the sine portion of it? So according to this angle, do I want the portion along the x-axis, is that going to be the cosine portion or the sine portion? What do you think?
Cosine.
Cosine, good. So this is going to be cosine of 30 degrees, right? Now, Coulomb's law tells us that F31 is going to be the same thing as K times Q3 times Q1 divided by the distance between the two, which in this case is going to be this distance, which is what we call R13 squared times cosine of 30 degrees, right? So this is my x components. Now, if I plug in my numbers, what I find in this case then is that the x component works out to be about 120 newtons. So this is equal to 120 newtons. Okay. Seems okay? So let's look at the y direction. So now we can do F3y. So F3y then is going to be F31 in y portion plus then F32 y portion. Right? Now in this case, according to our picture, F31y is pointing in the negative direction. So this is going to be negative F31 times sine of 30 degrees. Right? Because if this one's cosine, then I want the sine portion, which is this portion. Plus all of F32, because F32 only points along the x direction, or sorry, along the y direction. Okay? So now we want to do is now use Coulomb's force or Coulomb's law here and here to rewrite these in terms of K's and Q's and R's and all that good stuff. So this is going to be equal to negative K times Q3 times Q1 divided by R13 squared times sine of 30 degrees plus K times Q3 times Q2 divided by R32 squared. Or R23. Either one, same thing.
Wait, I'm sorry, why did we cross out F31Y?
Oh, I didn't mean to. It's just when I was moving my pen, it.
Oh, okay.
Yeah, just when I was moving the pen, it decided I was going to make a line. There we go. Sorry about that, Kelly. Good. Okay. So good. Let's plug in our numbers. What we find in this case then is that this works out to be about 260 newtons. Okay, so it's 260 newtons. So now we know that the X component is 120 newtons, the Y component is 260 newtons. So from here we can find the magnitude of the net force. So we know the magnitude of the net force, F3, is then by Pythagorean's theorem, this is going to be the X portion squared plus the Y portion squared, square rooted. So in this case, this is going to be 120 squared plus 260 squared, square rooted, which in this case works out to be about 290 newtons. So this is 290 newtons. And remember, a vector needs to have two pieces of information, needs to have, at least in 2 dimensions, needs its magnitude and its direction. So for the direction, we have the angle, let's call that angle 3, is then equal to the inverse tangent of then the Y portion divided by the X portion. So in this case, it's the inverse tangent of 260 divided by 120, which is equal to 65 degrees. Okay. Means okay. And then as a quick check, one thing we should always do and get in the habit of is always go back to our picture. So according to our picture, this is theta 3. So we always want to make sure that the angle that we get makes sense relative to the picture. That's one of the reasons that we draw the pictures. So here we can see that this is what? Greater than 0 positively, but less than 90. And from our angle, we found that it's 65 degrees, which is between 0 and 90, which it should be. So basically, we should always make sense that, again, that angle that we calculate makes sense. And in this case, it actually makes sense. Okay. Everybody's okay? Not too bad. So let's do one more example, assuming we have time here to do that. So let's look at this one, assuming PowerPoint wants to open faster this time. So this one says we have 2 particles fixed on the x-axis. The first of charge Q1, which is equal to 8 times Q, whatever Q is. So Q is just some charge amount, which is located at the origin. And the second one has a charge of Q2 time equal to -3 times that same amount of charge Q, which is located at a distance of L away from the x-axis. So on the positive side. So it wants to know at what point, other than infinity or infinitely far away, can a third charge, Q3, which has a charge of 5Q, be placed so that it's in equilibrium. So in this case, what we want is static equilibrium. So let's kind of draw what's going on here. So what we have in this case then is at the origin. So let me say this is my origin. I'm putting Q1, which has a charge of, what was it? 8 times Q, again, whatever Q is. So 8 times Q, looks like 86. There we go, get rid of that. So 8 times Q. We have another charge over here on a positive x-axis. So let's say here, this is Q2, where the distance between these two is some length of L. Okay, so this is my y-axis. This is then my x-axis. And this one has a charge of -3 times Q. So now what we want to do is we want to take some other charge out here. Let's call that Q3, which has a charge of what was it, 5? Yeah, 5 times Q. And we want to know where can I move this thing to? So either somewhere here, or somewhere here, so that the total force on the third charge is equal to 0. So this is what we want. So we want that the net charge, or the net force on charge 3 is equal to 0. So let's think about this before we actually put it somewhere. So let me call this region 1, let me call this region 2, and let me call this region 3. Okay. So first question is, can we put Q3 into region 1 and have it experience 0 net force? So what do you think? So could I put this guy here, anywhere in this region, and have it experience 0 net force? So what do you think?
I don't think so, because Q1 and Q3 are both positive, so it would create a repulsive force, wouldn't it?
Good. That's right. So let's keep going with that. So here, you're exactly right. So we have Q1 and Q3 are both positive, so that's going to experience a force in this direction, right? Repulsive force. So this is going to be F31. But simultaneously, this one is a negative force, which means it's also going to feel a force in this direction of F32, which is an attractive force. But what's different? So here, I have an 8 times a 5, which is bigger than a 5 times a 3. So the numerator is bigger. But what's also true? If I put this guy here, this distance is also going to be smaller than this distance, right? And if we think about Coulomb's law, so again, Coulomb's law is equal to, say, Q1, Q2 over R squared. What's happening is, if I put it here, I have a bigger numerator and a bigger denominator, or a smaller denominator, which means that this force here is huge compared to this force, which means that, no, I couldn't put this here because overall, this is a large force, this is a small force, it's going to feel an overall force in this direction. Right? Everyone's okay with this? So the overall force on F3 would be to the left. What about out here? Well, out here, it's the same thing, basically. So what's going to happen here is if I put it here, what will happen then is this is going to feel an attractive force here. So F3 is going to feel a force in this direction by 2. But Q1 is going to result in a repulsive force, which is going to push it in this direction. So even though the numerator is bigger between these two forces as opposed to these two charges, this distance is so much bigger than this distance that overall that distance is going to take into account, which is going to feel an overall force in this direction, which means F3 is going to be pulled in this direction. So ultimately, it can't go in this region either. Because out here, it's going to feel a repulsive force in this direction, oops. Out here, it's going to feel an overall attractive force. Well, what happens if I put it here? Well, if I put it here, what's going to happen then is what? It's a positive, which means it's going to feel a repulsive force in this direction from 1. But, let's see here. So where am I? Oh, no, sorry. I lied to you all about everything out here. Good. Sorry. I was listening to my kids banging on things and kind of got sidetracked. Okay, so actually, let's go back to what we said over here. So over here, so I'm going to have an F32, again, pulling in this direction. I'm going to have an F31 pulling in this direction, which means that here I have forces in opposite directions. So actually here it can exist. Sorry about that. So in region 3, this thing can actually exist. Where over here, I have a repulsive force, but I have an attractive force here, which means that here it's going to overall feel a force in this direction. Sorry about that. So good. So this region, it can exist. This region, it also can exist. My kids are screaming. So over here, it can actually exist because here it's going to feel an attractive force and a repulsive force, which means somewhere in this distance, it actually can exist. Okay? It can be placed to have a total net force equal to 0. So first of all, we learned that what? Here it can't go in because it's going to feel an overall repulsive force. Here, it can't exist because it's also going to feel a force being attracted to Q2, which means the only place it can actually exist is in this region where it has both an attractive force and a repulsive force, But again, from here, it has a bigger numerator than from here. But again, it has a much bigger distance from here than it does from here, which means that that'll overcompensate for the denominator going on here. Okay, so we'll re-talk about this on Tuesday. So let's leave it at this stage. So we'll actually go through it since we're out of time at this stage. And so I can go beat up my children. You're both coming in now, huh? Come here. Bye. Yep. Okay. Say goodbye to everybody. Have a good weekend. Good luck on your test.
Goodbye.
Yeah, I know. Okay. Oh, wow. Look at all of that.